Okay, class, welcome to chapter 3 of Journal 1. So we're going to do concavity and higher order derivatives. And these are going to be extensions of ideas you already know. So your toolbox of differentiation rules that we had been putting over there, we're not going to add to that, but we're going to use it. And the first thing we want to take a look at is do you remember this function? This was our road trip function. Remember, we all got in a bus, took a trip from Charleston to Raleigh, and this described our behavior over time, our position, our distance from Charleston over time, where x was time in hours, f of x was our distance in miles from Charleston. And we know how this is a very easy function at this point for us. If you saw this on a quiz or a test, you'd be super excited to take the derivative of this. No problem, just a couple power rules, linear rule, sum rule, but at this point we don't even think in rules for something this basic. 10x plus 50. And we said again that this derivative represents the speed that we're traveling then. In speed, which is also, if you've had some physics, you might talk about it as velocity. And now in this chapter, we're wondering what happens if we take a derivative of this. A derivative of a derivative, and it's called a second derivative. And it's denoted with two little prime marks, f double prime we usually say. And again, very easy to do this, a linear function, a constant rule, 10. And then we wonder what would happen if we just keep on going. We could take a third derivative, three little primes. Derivative of a constant is 0. We could take a fourth derivative. Derivative of the constant is 0. And we just see after this point, we just keep getting 0. So the 5th, 6th, 7th, and so on, derivatives are 0. It doesn't always happen for some functions. I know we're not doing sines and cosines and trig functions in this class, but just to give you an example of one that has very different behavior, the sine function, its derivative is cosine. The derivative of cosine is minus sine. And then we could just keep on going in this manner, and we're never going to get something where they just all go to 0. We're just going to keep flip-flopping between these sines and cosines. So this will be negative cosine x. The fourth derivative, which sometimes we write in Roman numerals in a superscript, would be positive sine x, and then we're back to the beginning, and we take the fifth derivative, and we'd be back to cosine x, and it would just continue on infinitely, which again kind of makes sense. And if you remember a little bit about trig functions from high school, is that they are periodic and they continue infinitely. We do see that pattern here. Okay, so a couple morals at this point. We can take higher order derivatives, second, third, fourth. We're almost always going to be focusing though on these in this class. We know we could do higher ones. If you happen to take another, maybe an econ class, or certainly in physics and the general sciences, you'd see maybe uses of higher ones. Second thing, if this function represents position like it did for a road trip story, the first derivative is velocity. The second derivative is, again, if you might remember from high school physics class, that would be acceleration. Then the rate of change, so back to the beginning, the position, the rate of change of miles per hour is how you get to your first derivative. Then you're taking the rate of change of miles per hour over hour. So that'd be the rate of change of miles per hour squared. That's a unit of acceleration. Think about meters per second squared. Again, you often use that. If your distance was measured in meters, your time was measured in seconds, acceleration was meters per second squared. The third derivative would then be meters per second cubed, or miles per hour cubed. What does that mean? Well, it's a rate of change of acceleration. How fast you're accelerating, the rate of change that you're accelerating with. There's actually words for these. Again, we don't study these, but you might say that this is called jerk, and the fourth one's called jounce. Maybe if you learn to drive stick shift, or you sat in a car with someone who's learning to drive stick shift, this jerk might have some relevance or meaning for you. A rate of change of acceleration is jerk. Okay, but again, back to the original three, the function, its first derivative, its second derivative. We can tell quite a bit about a function's behavior from these three functions. And again, they're all functions. The original function, the derivative function, the second derivative function. give me an x, and they spit out certain things. In this case, the f of x spits out a height on the graph, a distance y, right? The derivative spits out a steepness of the graph, a slope, how steep you are. And then the second derivative is going to spit out something about how curvy you are. If you're curvy or not. You might be linear, and it'll tell you that. It'll say there's not much curviness. So those three things measure different things. You input an x, and they'll spit out how tall you are, a height on the graph, how steep you are with the first derivative, and how curvy you are with the second derivative. Okay, so another summary idea here. You're going to read through the first 3 pages of the chapter and do some activities that are going to get you to the place where you understand that the second derivative has to do with concavity. And you're going to see the derivations of this when you do your pages in the journal. First couple pages in chapter 3 of journal 1. Concavity, again, tells us something about the curviness of it. And we have 2 types of concavity. We have concave up and concave down. So we want to make sure we define our terms and we understand what these terms mean. That's a big part of business calculus, is making sure you know your vocabulary. So at this point, you should have a vocabulary list of words from chapter 1, from chapter 2, and now into chapter 3. These are our first few. Concave up and concave down. So a function that is concave up, sometimes this is abbreviated C up, which looks like the word cup, which helps you remember that it's something that has this shape, a graph that has this, it also looks like a smile. You see that a lot. Or part of a smile. It doesn't have to be the whole smile. It could just be one part here or one part over that half. All of those are concave up, as opposed to concave down, which looks like a frown. So hopefully you can remember that rhyme. Concave down, a frown, they rhyme. It's a frown or part of a frown. So it could be part like that, part like that. Those are all instances of concave down. So if I had a function like this classic function we talk about a good bit in this class, y equals x cubed. And I asked you, tell me the parts of this graph where it's concave up, shade them maybe. So it's concave up right here at the origin, and then on. All the way up, it's going to continue and be concave up. So another way of describing that is it's concave up on the interval from 0 to infinity. And you don't necessarily have to include the 0 either, because at 0, it's neither concave up nor concave down. It's going to be something else we'll define in a few more videos. And then in this case, everywhere else that it's not concave up here. So it does have concavity in the other direction from minus infinity to 0. Okay, now what do you notice about these sections where it's concave up? Let's focus on the shaded part here. If I stop and draw a tangent line at any point in this interval from 0 to infinity, I stop here and draw a tangent line, stop here and draw a tangent. You keep on doing this. What can you say about the slopes of those tangent lines? It's always the case, and we'll draw, maybe let's draw another function over here. Maybe put one above it. And we'll draw tangents on that one. Let's draw a more interesting function than just x cubed. And we don't need an explicit algebraic representation. Let's just say, let's plan as if you were making the profile of a roller coaster you'd like to ride. So maybe it starts off slow, it's going, cranking uphill, a big drop. Right, maybe that's the roller coaster we designed. And then the question is, this is y as a function of x. It's not given with an explicit algebraic expression, it's just given pictorially. And then I said shade everywhere on this graph where it's concave up. So pause the video, take a moment, do that yourself, and then we'll check it together. And it's concave up on any part that looks like a smile or part of a smile. So we start off here and we're smiling until maybe about there. And then we start switching to a frown. And then maybe about here we start smiling again, about there. That looks good, like it. So it's concave up on all of these intervals. And if we had an XY graph, let's say here, these could be defined at certain points. Maybe that's the point A, whatever that value is, B, C, D. So you could write all the intervals on which this thing is concave up. But every time, if you pick any point in any of these intervals, from 0 to A, from B to C, from D to E, from F to G, and stop and draw a tangent line, every single one of those, what can you say is in common about these? Okay, well, you can't say that they're always positive. They look like here they're always positive. But now we start here, yeah, they're positive, and then they get steeper positive. Then they start negative, and then they start positive. Negative, shallow positive, really steep positive. Really steep negative, shallow negative, 0, and increasing all the way up positive values that get steeper. And what you can say is that these, when they go negative, they actually go from negative numbers to positive numbers to steeper positive numbers. So we can actually say that the F primes, so it's always the case when you're concave up, that your F prime is increasing. Which is another way of saying that your second derivative is greater than 0. If your first derivative is increasing, that means its derivative must be positive. So again, think back at what it means to be increasing. F, the function f is increasing, means that its first derivative is positive. So now when we change from the function f to the derivative and say it's increasing, its derivative must be positive. So this is the key connection, that your concave up means your second derivative is positive there. Your concave down, if what? If you had to take a guess, if your second derivative is negative. Okay, so those are the key points from this lesson. We can take higher derivatives. Given a function, we can take its first derivative, its second derivative, its third derivative. The ones we care about are f, f prime, f double prime. This second derivative gives us information about the curviness of a graph, how steep it's changing. There's two types of concavity, or this bendiness that we described. We talk about when something's sort of bending up, it looks like a smile or part of a smile, full smile, sort of lopsided one, but that's fine. Or concave down when you're part of a frown. These are connected to information about the second derivative, or vice versa. If you have information that your second derivative is positive, you know your function must be concave up at that point, or on any interval where x has that second derivative as positive. Okay, so next time we're going to figure out, given a function where rather than just drawing it, we have some explicit expression. Maybe it was x to the 4th minus 3x cubed plus 2x minus 7. Right? We'll be able to find out the intervals where it's concave up and concave down with our next video.